Next we want to deal with derivatives of trigonometric functions. Now remember, we already have the derivative of sine is cosine, and we already know the derivative of cosine is negative sine. So based on these, we can kind of develop some of the other derivatives of the trig functions. So let's take tan x, for instance. The beauty about tangent is we can rewrite this as sine of x over cosine x. Now we have a quotient of functions. So our high function would be sine x, our low function would be cosine x. Now we can't really simplify this anymore, so we do want to identify our derivative of the high and the derivative of the low. So d high is cosine x, and d low, derivative of the denominator, is negative sine x. Alright, I want you to go ahead and put this into the quotient rule. Okay, so go ahead and write that out here. So go ahead and pause the video and then come on back. Alright, welcome back. So here you can check if you did low d high minus high d low over low squared. And let's go ahead and simplify this now. So here we have cosine x times cosine x, and this is cosine x squared. And we're going to write it like this. Now here we have minus and a negative, so that actually becomes plus, and this is going to be sine squared x, and then this is all going to be over cosine squared x. Now if you think back to your trig laws, we actually have a Pythagorean identity right here. What is cosine squared plus sine squared? Well, that equals 1. And if you ever forget these, just look in the back cover of your book. It's got a lot of good stuff in there if you're ever dealing with simplifying trig functions here. And then this is going to be over cosine squared x. And if we wanted to write this, the reciprocal of cosine, remember, is secant. So this actually is secant squared x. Alright, let's go ahead and fill in some of our trig functions here. So again, sine x is cosine x. Cosine x is negative sine x. Tangent x is secant squared x. Let's go ahead and do cotangent x. So remember, cotangent would be the reciprocal of this, and you actually get negative cosecant squared x. For secant x, this becomes secant x tan x. So that's the derivative of secant. And so then the derivative of cosecant, which is just the reciprocal here, is going to be negative cosecant x cotangent x. So you might want to take a little bit of time to commit these to memory so that you'll be able to do some of these trig functions. Alright, so our example is find the derivative of each function. Here we have y equals x minus tan x. So this is just a difference of functions, so we can do the derivative of x is 1 minus the derivative of tangent, which is secant squared x. And some of them will be just that simple. Our next one, we have x times secant x. And this right here is two functions being multiplied together. So we actually have the product rule happening here. So we have f of x is x, and its derivative is 1. We also have g of x is secant x, and its derivative is, well, we just learned it right up here, secant tangent. Okay, so let's go ahead and apply the product rule now. So 1d2, so x times d2 secant x tan x plus 2d1. So 2 is secant x, and d1 is just 1. So if you look at this, we have a secant x factor in both of these. So we're actually going to factor that out. And then we're left with x tan x, and then plus 1. And here would be your derivative. Alright, let's move on. Alright, let's take a look at letter C here. So again, I see two functions. So f of x is going to be sine x, and f prime is going to be cosine. And then looks like g of x is cosecant x. That's going to make g prime equal to, let's see, so the derivative of cosecant is negative cosecant cotangent. So let's go ahead and put this into our product rule. So y prime is going to be sine x times negative cosecant x cotangent x, so that's 1d2, then plus 2d1, so cosecant x times cosine x. Now this is pretty interesting. Here we have sine x times cotangent x. What if I were to rewrite cotangent x in terms of sines and cosines? Well, I'd have sine x minus cosecant x. Cotangent would be cosine x over sine x. And then cosecant x times cosine x would still be there. Now what does that do for us? Well, you can see now we have a sine x and a divided by sine x, and those actually cancel. So we're left with negative cosecant x cosine x plus cosecant x cosine x. So we have now a positive and a negative of exactly the same thing. So they actually cancel each other out, and we're left with 0. Now, it equals 0. Let's take a look at our original function again. It was y equals sine x cosecant x. Now remember I said, well, if you can multiply these and come up with one function, why not do that? Well, so what we can do here is we can rewrite cosecant x as 1 over sine x. Now do you see it? Sine x times 1 over sine x is just 1. And what's the derivative of 1? 0. So, you can see that it matches. One way was much shorter. So again, before you try product rule, see if you can't reduce it down to one function which would make this a lot easier. Alright, let's move on. Our last topic of the day is higher order derivatives, and this is a fairly simple topic, but if we look at it, the derivative of f of x is f prime of x, and we call this the first derivative of f of x. Now, we can take the derivative of f prime of x and we call it f double prime of x. And this is the second derivative of f of x. So got it? First derivative is just taking the derivative. The second derivative is the derivative of the first derivative. So look at this one. The derivative of f double prime of x would be, well, it would be f triple prime of x. And we would call this the third derivative of f of x. Now the derivative of f triple prime of x is, well, no, it's not f quadruple prime. Once we get to 4, then we go ahead and put this in parentheses as an exponent. So it's f4 of x, and this is the fourth derivative of f of x. And right here you can see some notation for any higher order derivative. So the nth derivative of f of x is y to the n, or we can write it f to the n of x, or we can write it d to the n y over dx to the n, or you can see d to the n over dx to the n of our function, or we can use this notation right here. Mostly we'll probably be using this or this or this right here. So let's go ahead and find the fifth derivative of y equals 2x to the 7th minus x to the 5th. So we'll find our first derivative using the power rule. So 2 times 7 is 14, x decreased by 1 to the 6th minus 5x to the 4th. Okay. Y double prime then is going to be 6 times 14, which is 84, and that'll be x to the, lower that by 1/5, minus 4 times 5 is 20, and then x to the, lower that by 1, we get third, so on and so forth. So go ahead and find y triple prime. Go ahead and find the fourth derivative, and then go ahead and find the fifth derivative. When you're done, come on back and check your work. So pause the video. Alright, welcome back. So you can check your work on the multiplications there, and this is your fifth derivative. Go ahead and try letter B on your own. So find the fourth derivative for y equals sine x. Pause the video, come on back when you're done. Alright, welcome back. So it's kind of interesting as we go through the sine and the cosine, because it keeps flip-flopping back and forth, and then the negatives. And so the fourth derivative is actually exactly the same as the original when we talk about sine. So what do we need higher order derivatives for? Well, here's one application of higher order derivatives, and it's in dealing with position, velocity, and acceleration. So if our position function is s of t, our velocity function v of t is going to be s prime of t, and that's the instantaneous rate of change in position, and we talked about that last class. Now if we take the derivative of velocity, we get acceleration. So the acceleration function is going to be the first derivative of the velocity, but that's also the second derivative of the position function. So if we want to find any acceleration function given a position function, we just have to find its second derivative, and that's the acceleration. And what acceleration is, it's the instantaneous rate of change in velocity. So a rock is dropped on the moon and has the position function s of t equals negative 0.81 t squared plus 2. And the position is in meters, and our time is in seconds. So it says find the velocity and acceleration functions of the rock after t seconds. Well, our velocity function v of t is going to equal the first derivative of the position. So the derivative here is going to be 2 times negative 0.81, which is negative 1.62, and then t, and that decreases by 1, and then plus 0. So there's your velocity function. For acceleration now, remember this is going to be the derivative of the velocity. So the derivative here is just negative 1.62. So question B then says find the velocity and acceleration of the rock after half a second. So we let t equal 0.5. So we want to find the velocity after half a second and the acceleration after half a second. So all we have to do now is plug these into our functions. So negative 1.62 times 0.5. So after half a second, the rock, the instantaneous velocity, is negative 0.81 meters per second. The acceleration function is just a constant now, negative 1.62, so there's nothing to plug in. So we have meters per second squared. All right, so that is product rule, quotient rule, and our higher order derivatives as it relates to position, velocity, and acceleration. Thanks again for watching, and I look forward to seeing you all in class.